Okay, welcome back. Today we're going to be talking about torque. This is the lead into all the other rotational motion stuff that we're going to talk about. Rotational kinematics is important, but torque is probably more important than that, okay? Because without torque, we really can't do any of the rest of it. Torque by itself, actually pretty straightforward. However, it is fundamental. It is very important that we know how torque works and we're able to solve problems about torques on different objects. So let's start. The definition of a torque is pretty straightforward. It is a twisting or rotating of an object as a result of a force applied to it. Okay? A twisting or rotating of an object as a result of a force applied to it. So, next question, well, okay, it has something to do with force. What factors affect how much an object twists or turns? And in order to do this, what I need to do is show you, I need to do a demonstration. Now, in class, this is very easy for me to do. Okay, I know exactly what to do in class. I'm going to kind of improvise a little bit here, so you're going to have to go with this for a little bit. So let me grab something here. I'm going to take the camera. We're going to move this. Okay, so let's get this set up the right way. Move this back. Okay. So what you're seeing here is my laptop. Okay, it's open right now. And the question that I'm going to give you is, if I want to shut this laptop, what would be the easiest way for me to do so? Okay. And this is not as kind of dumb of a question as it sounds. This is something that's actually kind of important to understand about how torque works. So I can ask a bunch of questions. Oop, disk drive's popping out for some reason. I can ask a bunch of questions about this, okay? Would it be better for me to use a small force to shut it or a larger force to shut it? What would make it shut easiest? And obviously the answer is larger force. But there's some more questions involved than just how big does the force have to be in order to shut this. Another question is, well, where should I put that force? Because if I put the same force here as opposed to here, think about it. Wouldn't I have to push a lot harder here in order to shut the laptop, whereas up here I can shut it fairly easily with just one finger? And even more so than that, let me try and reopen this. If I were to, so this compared to this, it's easier to push up here. What if I were to push down here with one finger? Okay, I'm not going to close this at all. All right, I'm pushing pretty much as hard as I can with this one finger. I'm not making any headway. Whereas if I push as hard as I can with one finger here, very easily closes for me. Okay? So, the difference between these points happens to be the distance between where I'm applying the force and the pivot point, right? The laptop screen pivots about this axis right here, okay? Going along this bottom edge. The farther I push away from that edge, the easier it is for me to close it, the more twisting or rotating that this screen does. There's one other factor I want to talk about other than just distance from the axis of rotation, okay? Even if I put my force up here, is it going to be very easy for me to close the laptop if I push down like this? No, it's not going to close at all. Matter of fact, even if I push like this, it's not as easy for me to close the laptop as if I pushed this way, okay? So there's something about the angle at which the force is applied relative to the distance, or displacement, I should say, from the axis of rotation. So causing something to turn actually has a number of factors in it. It's not only how hard you push or pull, it's not only the size of the force, it's also where that force is applied and the angle at which that force is applied. Okay? I'm going to set you back up so we can go back to the notes. Okay. Thank you, computer. Okay. let's get back to it. There we go. All right, so what factors affect how much an object twists or turns? Well, we just saw all those different factors very briefly. We saw that one of the factors was how strong the force is, the magnitude of the force. I don't need a question mark there. We saw that one of the other factors, which was a little surprising to us, is where the force is applied in relation to a pivot point. And the technical term for pivot point is axis of rotation. Axis of rotation is what the object rotates or twists around. And the last factor is the angle at which the force is applied. Those are the three factors that affect how much an object twists or turns. Okay? So, or how much turning or twisting there is due to a force, I should say. Okay, well, if I was in class, what I would have done to show this, and you can try this at home, actually, I just don't have any of these things here with me. In class, what I do is I take a meter stick and I balance on the meter stick at different points a mass, like a 1 kilogram mass. So I grab the meter stick at like the 0 end and I put the mass on, let's say, 10 centimeters, very easy to hold up. I move it up to 20 centimeters, it's a little bit harder. Move it up to 30, 40, 50, 60, and by the time it gets to 60, either I'm going to drop the meter stick or that meter stick is going to snap. And that's because there is now a larger twisting or turning impulse on that meter stick because the force that is on it, the weight from the little mass that I put on it, is now farther away from the axis of rotation. The axis of rotation is where I'm holding it, okay? I also show the same thing, and you can do this at home very easily with a door. Why do we put door handles away from where the hinges are? Well, it's because to make them easier to open. If you put a door, think about it, if you put a door handle where the hinges go, you'd have to pull or push really, really hard to get that door to open, okay? Go to a door at your house and push and pull on it at different spots, and you'll see that some places it's easier to turn the door than others, okay? Door handles actually are the same principle. Why do we make door handles that are elongated? So that we can, well, put our hands far away from the rotation axis and turn them easily. So, these are the factors that affect how much a force causes an object to twist or turn. So what we would say is these are the factors affecting the size of the torque. I'm going to give you the equation for torque right now. That equation looks like this. It's got a symbol you're not familiar with. Okay, now I'm going to define all these things. So this kind of weird looking T thing, almost looks like half a pi symbol, is, well, it's the Greek letter tau, T-A-U, and what it stands for is torque. Okay, this is the symbol for a torque. And a torque is equal to R times F times sine theta. Now, R is a little bit different. It seems like R is kind of like a chameleon. It always has a different definition. The definition of R is the distance from, I'm going to abbreviate this AOR, the axis of rotation to where the force is applied. How far away the application point of the force is from the axis of rotation. So with the computer example, axis of rotation was at the hinges where the computer shuts or opens. When I was pushing at the top of the laptop, at the top of the screen, that was a much bigger distance, or I should say displacement, much bigger displacement away from the axis of rotation than when I pushed in the middle of the screen or at the bottom of the screen. Okay, so that R is important. F, very straightforward, is the magnitude of the force. Obviously, how big the force is plays a big role. theta, the sine theta part is important. Just like when we said work equals FD cosine theta, and we said theta in that equation is the angle between the force and the displacement, this theta is very similar. It is the angle between R and F if each vector started from the same point. In other words, if they were tail to tail. You guys should know what tail to tail is, okay? The arrows are pointing away from the same point. So even if the force and the displacement vector are not tail to tail in the actual drawing, the angle here is the angle that would be between them if you were to draw them that way, okay? If you were to draw them so that they both started at the same point. And we'll get lots of practice with that, okay? Let's see, a couple notes that I want to make. All right, so something about the axis rotation, okay? A kind of a neat hint, which we'll see many times as we go through this unit. And we're just going to write it down now so that we get it in our heads. You have the option to choose the axis of rotation if the system is in equilibrium. Okay. A couple other housekeeping notes. A lot of times, so you notice that it was easiest for me to close or open the laptop when my force, okay, the direction of my force was at a right angle to the direction from the displacement vector from the axis of rotation to where I was applying the force. Okay, when I pushed straight down on the laptop from above, it didn't cause any rotation. When I pushed at a right angle, it did. And if you think about how sine theta works, that should make sense. Sine theta is at a maximum at 90 degrees. So when something is at 90 degrees, when something is at 90 degrees, that generates the biggest possible torque, okay? Most cases you're going to have the sine theta, the angle between R and F is going to be 90 degrees, but you shouldn't always assume that. If this angle is not very obviously going to be 90 degrees, you're going to use what I would call the line of action. And we're going to talk more about that tomorrow. Okay, you're going to use a line of action in that case. All right, so this is a lot. We still got some more to do. Let's talk about the units for torque. The units, well, R and F. R is measured in meters. F, the force, is measured in newtons. And sine theta, that just gives us a number. So the units end up being called Newton meters. Now there's something else that you've seen this year that could have units of Newton meters, and that would be energy. This is not the same unit as energy, okay? A Newton times a meter in this case is not the same as a joule. Please do not write your torques in terms of joules. That is going the wrong way. It's more than I care to get into right now why it's not a joule. You're going to use Newton meters for your units here. And last thing, just a bit of convention. If a torque causes an object to rotate clockwise, that torque is negative. A counterclockwise torque, on the other hand, is a positive torque, okay? So if you've got something that's rotating this way, okay, that's counterclockwise, that's considered a positive torque, actually. If you've got something that's rotating clockwise, like this, sorry, I had it wrong at first, that would be a negative torque, okay? That's just a convention. That's like saying up and right are positive. That's just what most people do. It doesn't have to be that way, but that is the convention that most people will use, okay? Real quick, let's talk about how does this relate to linear motion, okay? Yesterday, we talked about how linear motion and angular motion are similar. We talked about how we can measure the same sorts of quantities in linear motion, and they have an analog in regular motion. In linear motion, we measure distances in meters. When we're talking about angular or rotational motion, we're talking about angles that objects rotate through. The symbol for that is theta. For v, the linear speed, how fast something covers ground in meters per second, we don't care about that in angular rotational motion. We care not how far it moves in meters, but how much of an angle it rotates through in a certain amount of time. So radians per second would be our unit there. And if you remember, the symbol is this omega thing, which I happen to call wumbo sometimes, but don't tell other people that. For linear acceleration, we have a. For angular acceleration, we have alpha. And to give you one more symbol, for linear, in linear motion, we have forces that cause objects to accelerate in a linear fashion. When we're talking about something rotating or moving in an angular fashion, spinning around an axis, we don't have forces. The analog is obviously a torque, a twisting motion. I'll be back in a little bit to finish up these notes. Bye.